Hey guys, welcome to this video on an introduction to the electric field. Hopefully, as the title suggests, in this video we are going to be laying the foundation, which we'll do both conceptually and mathematically, to understand what an electric field is. But I think even more importantly right now is actually just understanding what a field is in general. Now, electric fields and charged particles are ubiquitous. Everything's made up of them. But we don't really always think in terms of electric fields because it's something we can't really see. So I'm going to be using the analogy of gravitational fields a lot as we uncover these concepts to help us make these things more tangible. So if you ever feel a little bit lost or confused about the electric field, just try to think, okay, analogous to the electric field is the gravitational field, and that should usually clear things up. So before we actually jump into either of these specifically, we're going to talk about what a field is in physics in general. Now you can take whole courses in math and physics in fields and different kinds of theories, so I'm just going to give you some very basic information right now. One kind of field that we will encounter are scalar fields. Another kind of field that we'll encounter, and the one we're actually focusing on in this video, is a vector field. And when we're talking about a vector field, we've actually abbreviated the full term to field, but it actually is a force field in this case. So when we talk about the gravitational force field, we're talking about a vector field that describes the force of gravity in the space around Earth. So there's a little hint at the definition, is that a field is a physical quantity or value that describes a location in space. Now, it doesn't have to be in space as in where the stars are, right? It could be in the space around anything. So let's say you have a can of Coke placed on a table and someone's electrically charged this can of Coke. Well, you could describe the electric force field around the can of Coke or around the space surrounding the can of Coke. Now, this is a very vague definition right now. And so we're going to make it slightly more tangible by saying that when we're trying to describe a field around an object, in the location around an object, what we want to do is assign a value to the particular location. So right now our definition for a vector force field is a way to assign a value that describes a location in space around something. Well, it's still very, very vague. So when we talk about assigning a value, what do we mean? Well, it could be anything. Here's a really tangible example. And this is actually an example of a scalar field. Let's say I take a map of, let's say, New York City. And the map shows all the streets and buildings and so on and so forth. And at a particular time during the day, what I want to know is at every single location in the city, what is the temperature at every little dot on this map? What I'm doing there is assigning a value of temperature to locations in a particular space. This space being New York City, the locations being all the locations throughout the city or positions throughout the city, and the value being the temperature. So that would be an example of a scalar field, a temperature field that tells the temperature at every location in the city. But in addition to that, we might actually want to describe how that changes over time. So we could say this scalar field map of temperature shows you what the temperature is at every location in this particular space at every particular time. So it can become very, very meaningful and very useful to describe things as fields rather than individual values at specific places. So it's almost like having a more generic value to help us understand what the overall picture looks like in a certain space. And that picture could describe many different things. In the example I just gave of the New York City example, it would be the temperature at every place. So let's jump to the gravitational force field. What exactly are we assigning to every location in space? What is the value that's describing this location or that location over here, or maybe this location over here? Well, really, when you look at gravitational force field, what we're really doing is we're trying to say, okay, at this location right here, what is the gravitational force? At this location right here, what is the gravitational force? So the value is gravitational force, just like temperature was the value assigned to each location on the New York City map. Now, you might be thinking to yourself, well, you can't have a gravitational force at a location because in order to have a force, you need two things. And you're right, you're 100% right. So we're going to unpack that idea here in a second. Gravitational force is defined, as we've done before, as the universal gravitational constant times the product of two masses, let's call them mass 1 and mass 2, separated by some distance r. And what this describes is how strongly two masses attract one another, separated some specific distance. Well, there's nothing at this location right here, so how am I going to describe it if I only have one mass, being the mass of the Earth? Well, I'm going to call the mass of the Earth here mass 1, as in my example, and I'm going to give it a more serious name, and that name is source mass. So we call it a source mass because it's the source of this particular gravitational field. At all these locations around the Earth, there doesn't have to be another mass here in order for me to describe the gravitational force field. But I do need another mass at another location to describe specifically the gravitational force at the location. So how do we describe the force at a location if there's not another mass? Well, physicists and mathematicians are very clever, and they came up with the way to do that. We first define a gravitational force field as the lowercase letter g. And what we are going to say here is that g is not a value of the gravitational force at every location, but the gravitational force that would be exerted per unit of mass placed at that location. So let's go ahead and substitute in the gravitational force equation into this definition of gravitational field. So I'm going to plug in G times M1 times M2 over R squared, and then that needs to all be divided by mass. Now we already said M1 is the source mass. Well, M2 is the mass that I would place at that location, so that's going to be the same thing as this mass over here. So again, what we're saying is that the gravitational force field describes how much gravitational force would be exerted if I place an object here of X number of kilograms of mass, or per kilogram of mass. So you can see when I substitute the equations in, M2's both cancel out, and I'm left with the equation G times M1 over R squared, which is a really clever way to now say, yeah, I can actually describe how much gravitational force would be there per unit of mass placed. I don't have a mass there yet, but once I define what the mass is that's placed there, then I can know the gravitational field. So it's actually a very clever way. It eliminates the need for the little small mass, which we often will call a test mass. That's the thing that I would actually place at this location. So let me place a test mass there. I'm going to make it a satellite. And that little satellite right there would have a mass of M2. And once I've placed that particular mass there, then I can actually know what the gravitational force is that's exerted on that particular test mass. But before I've placed the actual test mass there, I can still describe the location as the amount of force the Earth would exert per unit of mass. So, to summarize where we are at so far, what we are saying is that a gravitational field is describing the amount of force that could be exerted per unit of mass placed at a particular location around the source mass. In terms of location, we would rather write it as G times the source mass, so I'm going to put a little s there, divided by R squared, with R being the position at some distance away from the object. Now, very easily we could figure out the units of the gravitational force field, because we know that force is measured in newtons and mass is measured in kilograms. And so we would have a Newton per kilogram describing the specific gravitational field at any point around the Earth. Another way that I think of this sometimes, and this is more of a scalar type example, is let's say you want to rent an apartment in a building, and they tell you, we aren't 100% sure which apartment we have available yet, but we can tell you that it costs, let's say, $100 per square foot if you want to live in this building. And you might ask them, well, what's my actual rent going to be? And they'll tell you, we don't really know yet because all of our apartments have different actual square footage, but we can tell you that you're going to pay $100 per square foot. So really what they're telling you is the force field or the money field equation per square foot. And when you actually have an apartment, analogously, when you actually have a second mass placed at the location, that would be an actual number of square feet, they'd be able to tell you how much your actual apartment costs. So gravitational field is more like the dollars per square foot idea. It's the amount of newtons per kilogram, like dollars per square foot. It hasn't told you an exact amount of force that an object's going to experience because there's no object there yet. It's just a location. Now, very quickly, because we have all this knowledge now, we can describe the electric field in a very similar way. Instead of using lowercase g, because that's for gravitational field, what we're going to do is actually use uppercase E as the symbol for electric field. And all we're going to do now is say that the electric field describes the amount of, not gravitational force, but electrostatic force that is exerted per unit of charge that's placed at a particular location. Now, we know the electrostatic force equation is K times Q1 times Q2 over R squared. And again, we have this Q here, and that, remember, is the little test Q that's going to, or test charge that's going to be placed at some location. So those two Q's cancel. So I can see that the electric field is defined as the amount of electrostatic force that would be exerted per unit of charge at a particular location. So it could be seen as K times Q over R squared. Now I made this an uppercase Q because we would refer to this thing as a source charge, just like the Earth would be our source mass. So you can see we can describe the location around this little electron now and say, all right, if you were to place a charged particle nearby this electron, here's how much force that electron could exert per unit of charge that you place there. So I can't tell you exactly how much force the thing you place here is going to experience, but I can tell you how much force it would experience per unit of charge that I placed at that location. To end this up, we're going to say that the units for the electrostatic or electric field are going to be newtons per coulomb rather than newtons per kilogram. So I highly recommend watching this and really trying to understand this concept of what a field is, because it plays a lot of helpful sense in describing the universe.